one of the reasons that the bearing goes bad is when so much heat is getting into where the bearing sit in a bearing housing. And extended surfaces design, fin designs, are an excellent choice to reduce the heat from our part. In this video, I will show you the formulation. I will drive a formula that will show the relationship between the change in temperature, the temperature of our part, and the surrounding air temperature, and the geometry of the fin. And by using that, we can easily design, what sort of extended surface design we need. So let's assume that our part, this is the edge of our part, and we have a temperature 10 here, and the temperature of the air outside, let's say, is T infinity. And what we want to do, we want to reduce the heat from our part, and we want to take that heat out and send it into the surrounding air. So for that reason, we are going to use an extended surface, or they also call it fin. So let's assume that this is our extended surface. And our assumption here is going to be that our transversal thickness is a lot smaller than our axial length. So what does that mean? That means that our temperature will be a function of x rather than a function of y. Now let's assume a control volume within this extended surface. Let's assume that this is our control volume. And let's assume that the thickness of this control volume is dx. And let's assume that the heat that is entering this control volume is called Qx, and the heat that exits this control volume, a portion of that will be on an axial length, will be Qx plus dx, and a portion of that will go into our surrounding air by convection heat transfer. Let's call that QC. So our Qx, the heat that is entering our control volume, will be equal to Qx plus dx plus QC. Now we can use the Taylor series, and we can write this portion as Qx equal to Qx plus d over dx, Qx dx plus Qc. Now we can rewrite this equation as Qx minus Qx minus d over dx, Qx dx minus Qc is equal to 0. Now here, Qx's will cancel out. We're going to have minus d over dx, Qx dx minus Qc will be equal to 0. Now, if we assume that our parameter of this control volume is P, so the convection heat transfer per unit area out of this surface can be written as, let's say, P QC dx, the parameter multiplied by dx QC. So here we can write this as minus d over dx qx dx minus p qc dx equal to 0. Now we can divide this equation by dx. We are going to have minus d over dx qx minus p qc equal to 0. Now here Qx is the heat transfer between a solid. So heat transfer in a solid is conduction heat transfer. So the formula for conduction heat transfer, Qx will be equal to minus Ka dt dx, where T is the temperature, K is the thermal conductivity of our material, and A is the area, is our cross section of our film. And QC can be written as, QC is the heat convection from solid to air, that can be written as H times T minus T infinity. So let's plug those values here. We are going to have minus d over dx times minus Ka dt over dx minus pH T minus T infinity equal to 0. Now, if we restrict ourselves to homogeneous isotropic material, and those are the material just like the slabs that you buy in Home Depot, you know, if we use something like that as an extended surface, so homogeneous isotropic, that means our K is constant. Our K is constant, so we can write this equation as minus times minus is positive. So, and since K is constant, we can bring it out, and we can write this as K d over dx times A dt over dx minus pH T minus T infinity equal to 0. So let's divide this equation by K. If we do that, K will be canceling here, and we are going to have K here. Now, let's assume that the difference in temperature from the temperature of a part to the surrounding air temperature, T minus T infinity, is equal to theta. Now, if we differentiate that, we are going to have dt over dx minus T infinity over dx equal to d theta over dx. So our air temperature, our outside temperature is T infinity, is in fact constant. So the derivative of a constant will be equal to 0. So that means our dt over dx will be equal to d theta over dx. So dt over dx is d theta over dx and t minus t infinity, we assume that this is theta. So this is the general formula that we can use to design our extended surfaces, our fin, in order to reduce the heat from our part. Now in this case, you know, if we buy in Home Depot a slab like that, let's say if we want to use this as a fin, the cross section is uniform, so the cross section is constant all over. So in this case, this is in a case that our cross section is not uniform. So this is a general formula. Now we can apply a special case when our cross section is constant. So when our cross section is constant, that means the fin that we are assuming is constant, is uniform cross section. So this is our fin. This is in the case of a slab like that. So here, let's assume again a differential volume, a control volume dx Now, in this case, if we call this side as B, this side as L, our area will be equal to B multiplied by L. And it will be constant in all the way. The cross section constant all the way, and our parameter will be 2 times B plus L. So in this case, when our profile have a constant cross section, this area will become a constant. So it can come out of this equation. So we can rewrite this equation as, for this case, we can rewrite this equation as A d over dx d squared theta over dx squared minus ph over k theta is equal to 0. So in this case, our area is constant, we take it out. Now we can again divide that equation by A. If we do that, A will cancel out here, and we are going to have A here. Now we have a differential equation that is relationship between the temperature difference T and outside temperature T infinity, and A, the geometry, and P is the parameter, the geometry and parameter, the geometry of our profile. So by using this, by solving this equation, we can easily design whatever system we need using the extended surface to dissipate, to reduce the heat from whatever part that we need to. Now, I believe I have posted a video how to solve a differential equation like this. So let me go ahead and solve this again. If we assume that this is m squared, so if we assume that m squared is equal to pH over AK, then we can write this equation as d squared theta over dx squared minus m squared theta equal to 0. So the general solution for a differential equation like this will be theta will be equal to C1 e to power mx plus C2 e to power minus mx, where m will be the square root of pH over AK. Now, if in this case we apply the initial condition, let's say as x0, when our x is equal to 0, our temperature will be 0, will be T0. If at x0 our temperature is T0, then our change in temperature will be T0 minus T infinity. So let's call that as our initial change of temperature, theta 0. Now as our x, let's say this is infinity, as our x reaches infinity, our temperature will be the temperature of the surrounding air, and our change in temperature will be T infinity minus T infinity, which is equal to 0. So if we apply these initial conditions, if we apply this condition to that differential equation, to this answer, we are going to have C1 will be equal to 0, and our C2 will be equal to theta 0. So our solution, theta will be equal to C1, it will be equal to initial change in temperature multiplied by e to power minus mx. So this is the solution to this differential equation. Now, now we can apply different cases. We can use the end result that we had and apply for a non-uniform, when this curve is a function of x, we can apply for cases like that. But the easiest way is the standard profile, easiest and cheapest, because usually all metal distributors, they have all sizes of these slabs in stock, and if you want something that is not uniform, you have to place a special order, so it's going to be harder in calculation and more expensive in design. So I hope you liked it, and if you are working on something like a custom-made part that you have certain amount of heat in one location that you want to get rid of it, this is what you need to use. And if you need any help, you can find my contact information in my website, nmdbearings.com. You can go there and find my contact information and send me a message. I will be glad to help you. Thanks.